Okay, so did you guys do the test, the n equals 1 case, I hope? Okay, so it's kind of a sentence that you write. It's not really an equation. So you just write 1 squared plus 1 is, or actually it's more of a question, is 1 squared plus 1 divisible by 2? The answer is yes. Okay, so step 1 in any inductive proof is to test the n equals 1 case. By the way, that's a little bit overrated. There is something called the extended version of an inductive proof, where you actually start by showing that n is 2 is valid, or n equals 3 is valid. You don't have to start at 1. But the reason we're starting at 1 on this is because basically they're saying that this rule works for any n, and the very first n that they're talking about is 1. So you usually start with whatever first n is mentioned. Okay? But if this had said, hey, prove that this is divisible when n is greater than or equal to 10, if this had been the problem, see, prove that it's divisible by 2 when n is greater than or equal to 10, then you would have tested n equals 10, see, as your first test point. Okay, so we're assuming they mean n equals 1 is the very first amount. That's why we're using that for Roman number 1. Okay, well that was simple enough. So now let's look at part 2. So part 2 of an inductive proof is to do the n equals k assumption, right? So n equals k. Assume n equals k case. So we're assuming that k squared plus k is divisible by 2. That's an assumption. By the way, there's a mathematical way to write that. 2 divides k squared plus k. 2 divides k squared plus k. This means k squared plus k is divisible by 2. So if you like symbols better, you can do that. So I'm just going to keep writing the sentence. Okay? Next step is set up the n equals k plus 1 case. So you get k plus 1 squared plus k plus 1 is divisible by 2, which unfortunately you're supposed to kind of plug in, you know, the previous line of work. You're supposed to kind of plug this fact into this newest sentence that you wrote. The problem is we don't see any k squared plus k's anymore. Do you guys see any k squared plus k's anymore? Maybe if we FOIL it out or something. Why don't we do that? Why don't we FOIL this out and see what it looks like after FOIL. So this is k squared plus 2k plus 1 plus k plus 1. I still don't see any k squared plus k's. Do you? I need k squared plus k's in my work, you see. I'm supposed to be replacing it with a phrase divisible by 2. You see what?
Can you just rearrange the numbers?
Yes. There's a k squared there and a k there. Okay, so let's steal this k from over here and put it in between. We'll insert it in front of, or right after that k squared. So now it looks like this. K squared plus k, right? Plus 2k plus 2. That's the guy I was looking for. I was looking for a k squared plus k. There it is. What do we know about k squared plus k? It's divisible by 2, right. What about 2k? You think that's divisible by 2? What about 2? Is that divisible by 2? Okay, so what we were saying is that k squared plus k is divisible by 2. By assumption. Right? Back in step 2a. So I can write that as 2 times something. Today I'm going to use 2u, u for ume. Because she looked really thrilled about this problem, so I just thought I'm going to pick 2 something, and I'm going to pick ume today. Okay, so 2 times something plus 2 plus 2k plus 2. What do you notice? They all have a what? 2, which means I can, yeah, pull it out. So now that you have this, don't forget, we're supposed to be writing the sentence every time. Oh, is divisible by 2, is divisible by 2, is divisible by 2, is divisible by 2. How much do you trust this last sentence? Oh, that should be a 1, not a 2. Some of you guys are wondering, like, how do we sort of factor out a 2 there? 2. How many of you believe that this expression is divisible by 2? Believe it completely, right? 100%? Well, then you can believe that if k squared plus k's divisibility led us to this fact, then these steps 2a and 2b are inseparably linked. They form a cohesive link. And that means that if it works for 1, which we already tested, then it has to work for the next number, 2, which means it has to work for the next number, 3, and this must work always. Okay, so here's what you're not allowed to do, okay? You're not allowed to say, oh, n squared plus n is divisible by 2. Well, let's plug in 3, 4, 5, 6, and sure enough, every time I do that, I get an even number. That's not a proof. That's you trying out a few numbers for n. That's not a proof at all, okay? So a proof always avoids numbers off the play. I'd rather use a 2u than a 200, you know? Because then it's more general, and that's what we need, a general proof. Any other questions? So looking for that little k squared plus k, we found it, yes?
So the u, is it 2u is equal to k squared plus k, or just u?
Well, when I got to this statement, k squared plus k plus 2k plus 2, I didn't need much proof to know that this and this were divisible by 2. But I need something that would defend that this was divisible by 2. Well, that was my assumption earlier. I can use my assumption in my step 2b. And so I wrote divisible by 2 by assumption. And then I wanted to give it a name. Like, what do you want to call something that's divisible by 2? Or 2 times something. So next time I'll pick 2a for Omar. But I just made that up, that u. And so that u actually represents half of k squared plus k. If I say, I'm thinking your number is divisible by 2, you should write down 2p or 2n. Because that's the kind of number Mr. is thinking of. Okay? After you see somebody do these a few times, you get the hang of it, and of course you try it on your own. When I first learned this, I was just reading textbooks and trying to figure out what they were doing. And like, it's really hard for a textbook to say, you know, where's the k squared plus k assumption buried in the statement, you know, and then Cecilia found the k over here, brought over. Like that kind of stuff's hard to type and write and read, but it's easy to talk about. Hey, where's the k squared plus k that we need so badly? Oh, there it is, we see it together. So it helps to do this as a class, I think. So if you didn't do too well on the homework, you didn't know what to look for. But you can now certainly do other ones. I had you skip some evens, you can try those. And since they're proofs, you don't really need to see the solutions. Any other questions on this assignment? Okay. Well, that's pretty good if you only had one question on that assignment. Proof by induction. Don't forget the Demov's theorem. We proved that yesterday. That's obviously important to Mr. Shore, and it was in the state standards up until Common Core. So Common Core, I don't know if they kept the Demov's proof or not, but that's always been a part of this class. So I'm trying to stick to the Common Core thing, but it's that particular problem I thought, even if they throw it out of Common Core, I think it's a good one. So I'm going to keep it for a while. Okay? All right. So you guys worked so hard to do some proofs there. I was thinking, we got these new formulas in our notes. Let's use them. Let me show you what I mean. Back on number 13, look at your homework number 13. You proved, hopefully, that 1 squared plus 2 squared plus 3 squared plus ... plus k squared is, or n squared is what I meant to say, is n times n plus 1 times 2n plus 1 all over 6. It was a tough one. I gave you permission to FOIL the right side if you needed. How many of you were able to finish number 13? Oh, good job. Okay? So if this is like a nifty little formula, it would be a shame to prove it and not ever use it, don't you think? Okay, so what I'd like to do now is just have you try it for 10. So I'm trying to see if you understand what the formula is allowing us to do. So we're going to turn number 13 into an actual notes example. Okay, so let's get out our notes. This is number 13 from the homework, and now we're going to use this as if it was a formula. So what I'm saying is, in number 13, you proved this thing, but you've never had the privilege of using it. So you kind of run the risk of creating a formula that you never even know how to use. What good is that? So I'd like you to find 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared using the formula. Can you identify what n is? 10. Correct. Use it. Okay, so if n is 10, this formula reads 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. Well, you shouldn't need a calculator for that. That's just 10 times 11 times 21 over 6. 21 is to 6 as 7 is to 2. 10 is to 2 as 5 is to 1. So this basically just becomes 385 because it's 55 times 7. So what is this formula giving us the ability to do quickly? To add the first n perfect squares. Now you studied numbers like 149, 16, 25, 81, those numbers are perfect squares. You studied those before as early as 3rd grade, 4th grade. But have you ever added them together? Probably not. Well, here is a nifty little formula to help you add them together. Okay? So we're going to memorize it. We're going to memorize it for next Thursday's test. So takeaway number 1, the first formula you need to memorize is, if you wish to add perfect squares, then you would use the last perfect square, the last number, times n plus 1 times 2n plus 1 all over 6. And we're going to memorize that. The sigma k squared, that just means you're adding 1 squared, 2 squared, 3 squared, 4 squared, and so on. Let's try another one. I'm going to give you a problem in sigma form, just to see if you can handle it. So, evaluate sigma k equals 1 to 13 k squared. If you wish, you can write out the first few terms, or you can just jump straight into the formula in red. What I don't want you to do is just adding them up on a calculator screen, It defeats the purpose of having a formula. Okay, so this formula is giving us permission to solve the entire problem using this upper number, 13. 13 is the key to the problem. According to this nifty formula that you proved last night, you can just solve this problem by doing 13 times 14 times 27 over 6. Why 13? Well, that's n. Why 14? Well, that's n plus 1. Why 27? Well, that's 2 times 13 plus 1. That is the answer. Pretty cool. Let's reduce it. So 27 is to 6, as 9 is to 2. The 14 and the 2 cancels to make a 7. So this time I'm multiplying 13 times 27.
63.
Huh?
13 plus 60.
What am I saying? 13 times 63. I was just seeing if you're awake. 13 times 63. $819. Can I get a witness on that one? Make sure I get the right number. I don't trust my arithmetic like I used to. So obviously I already did 7 times 9 and called it 27. So thanks, Amar. Is 819 correct? Okay, yes.
So whenever you plug in the numbers, it'll always simplify because you always get a whole number.
Yeah, you always get to get a whole number. Can you explain why?
Because you're always adding adding squares.
Yeah, the formula is providing us a shortcut for adding up 1 squared, 2 squared, 3 squared, 4 squared, 11 squared, 12 squared, 13 squared, right? So why would we get a decimal? There's no way, right? We're going to get a very large positive answer that's a whole number. Does that make sense? Okay. Now we're going to go and find this one. Now this is kind of a cheap shot for me to throw this problem out there. Example. Evaluate. Why is this kind of mean? What have I done to mess with you? Yeah, I multiplied in at 2. Like, I just gave you a formula for k squared, and now I'm busting out a 2k squared. How fair is that? Actually, it's pretty fair. The reason it's pretty fair is because the sigma means to add up lots of terms. If each term has an extra factor 2 in it, we could technically factor out this 2 completely out of the sigma. So we're going to pull this 2 outside to the front of the sigma. Remember, sigma just means add. So if you're adding a bunch of numbers that are twice something, you can pull out the 2 and multiply at the end. So what I'm saying is you can pull a constant out, a coefficient out of a sigma. That is perfectly legal. This is just 2 times the sum instead of a sum of twice something. Okay, let's bust out the formula and solve the sigma, and we will double it. So we kind of reversed the order of operations there. I'm going to add first, then double. Use the formula. You can solve this entire sigma using the 5. Just follow the formula. Okay, so Robin, what's the formula going to read if n is 5?
5 times 6 times 11 over 6.
Yes, this is n, 5. This is n plus 1. This is 2n plus 1. And there's a 6 there. This one simplifies pretty easily. The 6 cancels out. Okay, so the 6 just kind of crosses out, and we get 2 times 55. The answer in this one's 110. Pretty sure I trust my work there. Okay? And so this is the first takeaway formula, the k squared 1. So I'll write it one more time since it's way up at the top. If you wish to add the first n perfect squares, you can use the top number to do the whole problem. Just do n times n plus 1 times 2n plus 1 all over 6. And you should feel no shame using this formula because you already proved it. Okay? That's a nice feeling. Okay. Some of you said yesterday you don't feel any shame anyway using formulas you've never proven. You should feel a little shame. Okay, let's go to another something you did in your notes. In your notes, or your homework I mean, maybe you can tell me which problem it was, I can't remember. You proved that 2 plus 4 plus 6 plus 8 plus blah 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 plus 2n equals k, or equals n times n plus 1. N times n plus 1. Does this problem look familiar to you? You should have tried to prove it. Which problem was that? Was it the first one? Oh, okay. Thank you. So, this is a little bit awkward. Who would ever want to add up the evens? Well, you could. You could add up the evens, like you could add 2, 4, 6, 8. Who do we appreciate? You could just add 2, 4, 6, 8 by doing, listen. You could add 2, 4, 6, 8 by just taking 8 times 9. That's what this is saying. You could add 2, 4, and 6 by doing 6 times 7. That's what this is saying. Or no, I'm sorry, I'm taking that wrong. This is n equals 3. Yeah. You could add 2, 4, 6, the first 3, by doing 3 times 4. You could add 2, 4, 6, 8, the fourth of them, by doing 4 times 5. Okay? So n means how many you're adding. How many you're adding. You could add 2, 4, 6, 8, 10 by doing 5 times 6, because 10 is the fifth term. Does everyone understand the formula? Okay, I'd like you to do me a favor, divide both sides of that equation by 2. Divide both sides of that equation by 2. So if we divide by 2, we get 1 plus 2 plus 3 plus blah 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 plus n equals n times n plus 1 over 2. The reason I'm having you divide this by 2 is because I think you're more likely someday, maybe on the SAT in a couple months, or in a couple weeks, I think you probably will have the chance to add the first n integers. I could totally see that happening on the SAT. Add the numbers 1 through 25. Ready, goes. What is it for me? 25 times 26 over 2. Okay? Although I don't think they'd have you add odds. They would probably have you add just the regular numbers, 1, 2, 3, 4. Add the counting numbers. So this is our second formula that we're going to memorize. Can you write it for me in sigma form? This is our second formula to memorize. How would you write that left side in the sigma form? Go and write it. You can kind of cheat. Look back at my k-squared formula. It's very similar. Not the same exact sigma, but it's close. What goes on the left? We're not adding the perfect squares, so you shouldn't be putting a k squared in there. So what we'll do on that blank, it's not k squared this time, what is it? It's just k, right? See, the only difference in this problem and the previous one is the previous one said 1 squared plus 2 squared plus 3 squared plus 4 squared. This one just says 1, 2, 3, 4, see? So this would just be k. N equals 1, or k equals 1 to n. So we're going to memorize this formula. It's actually a little bit easier than the other one. Okay? Now, did you ever in your homework do this one? Did I give you this problem or not? I did not. The reason is, this one is a particularly difficult one. Okay? If you thought that, and if you thought the number 13 was hard on the homework last night, this one would have been real easy. It's a tough, tough one. You get down to step 2B, you're supposed to try and show that this left side, you know, for the n equals k plus 1 case, matches this formula, and it is tough. Really, really tough to do. So I didn't give it to you, but I want you to know it anyway. I just want you to not know the proof, but to know the formula, see? So the third formula, I'm just going to hand it to you on a silver platter without proof, and it looks like this. The sum of k cubed, as k goes from 1 to n, is n times n plus 1 over 2 squared. Memorize. Memorize. Okay, so let's summarize the 3 things Mr. Short wants you to memorize for the group quiz. Well, group quiz is open notes. But I mean for the next Thursday's test. Here it is. Ready? You want to memorize the sum of the first n integers is n times n plus 1 over 2. You want to memorize that the sum of the first n perfect squares is n times n plus 1 times 2, n plus 1 over 6. And you want to memorize the case for k cubed, n times n plus 1 over 2 squared. In green, those are the ones you need to have memorized. And we're not doing a note card this time. We've done 2 exams in a row with a note card, so we're done with note cards for a while, okay? All right? So don't ask this time, because I'll be fine to say yes. So I'm stating my note emphatically now. So I won't backpedal when you ask me. But these 3 formulas I think you should memorize. There may very well be a chance for you to add, 1 cubed up through 6 cubed someday, and you'll want a formula for it. Also, since we're doing inductive proofs, it's just a great time to bring this up. These 3. Do you see any connections between them? They all have the n and n plus 1. That helps us memorize. Okay. They all have a fraction, right? Huh? Yes, the numerator on the first formula is actually quadratic. So if you add linears, you get a quadratic. If you add quadratics, you get a cubic. And if you add cubics, you get a quartic. There's 4 powers of n here. That is not a coincidence at all. The antiderivative of a linear is a quadratic. The antiderivative of a quadratic is a cubic. And the antiderivative of a cubic is a quartic, as you'll find out in calculus. Okay? So that is extremely important. And it's a cool tie over. But another thing I noticed is the third formula and the first formula look almost exactly alike. Did you notice that? What's the only difference between the first formula and the third formula? Yeah. The third formula is just the square of the first formula. Just slap a square on the outside. So that makes it all the easier to memorize. And although it's hard to prove, it's not hard to memorize or use. Okay, so now it's time to play around with sigmas. Okay? So this segues into the next thing, manipulating a sigma. So the first thing I want to do is have you solve this problem, or we can discuss it, and you'll get something like this in the homework tonight, your last assignment. We're going to go k equals 1 to 12, okay? And we're going to solve 2k cubed plus 3k squared minus 4k plus 6. Whoa, that looks insane. Okay? Let me show you that it's not as bad as it looks. First of all, you could do this problem, I'm not going to lie to you, you could do this problem by plugging in 1, and then plugging in 2, plugging in 3, all the way up to 11, and then 12. You would have 12 numbers, you would then add them together, and that is the correct answer. But what's the fun of that? Okay? I mean, who really wants to find 12 cubed anyway? Not me. So what we're going to do is we're going to try and use our nifty formulas of the day. First, I want to understand that this is a sum of a sum. In other words, I'm adding up not 4 things, but a total of 48 things. When I plug in k equals 1, I get 4 things. When I plug in k equals 2, I get 4 things. There are 12 things to plug in and 4 each time. So there are really 48 terms altogether. Okay? There's nothing wrong with me splitting this into 4 problems, each with 12 terms. Let me show you what I mean. So I'm going to take this to mean the same thing as this. I'm claiming that this is the exact same problem. Why? Because whether I add the terms together first and then collect all the groups of 4, or whether I split this into 4 groups, each with 12 terms, makes no difference. It's all one big fat plus sign, folks. Everything's being added. And order of operations is totally irrelevant. The associative property, the commutative property, you can shuffle things around when you're adding, right? That's kind of what we're doing. So you can kind of think of it as me distributing the sigma to each of the 4 terms. Or you can think of it as splitting one summand into 4 summands. This thing is called the summand. This part is the summand. Okay? Okay. Well, for that matter, we could pull the 2 out of the first one, the 3 out of the second one, the minus 4 can be pulled out of the third one, and this last one is just 72 anyway. Why is it 72? Because it means you're going to be plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 into this expression 6. Well, there's nowhere to put the k. So you're just going to get 6, 6, 6, 6, 6, 6, 6, 12 of them. So the last one is just trivial. It's just 12 sixes added up. And I've given you a formula for this, this, and this. They are the 3 I asked you to memorize. Okay? So bust out your 3 formulas, and n is 12. See if you can do that with a calculator. N is 12. Try the 3 formulas here. The first one is the k cubed formula. So it's 12 times 13 over 2 quantity squared. We shouldn't even need a calculator to solve this, really. Maybe if the numbers get a little big, we'll use a calculator. The k squared formula is actually the most complicated of the 3. So it's going to be 12 times 13 times 25 over 6. Then the next one is the k formula. That's just 12 times 13 over 2. And then we have this plus 72. So I just stole the 3 formulas. The first one was n times n plus 1 over 2 quantity squared. The second one was n times n plus 1 times 2n plus 1 over 6. And the third one was n times n plus 1 over 2. It's stuck in 12. And now I'm ready to simplify and solve this. If I can do it without a calculator, that's great. If I feel like I need a calculator, then fine. But the whole point is not to just do the whole problem on the calculator screen. Maybe the last step or 2. Okay. So we basically have 2 times 144 times 169 all over 4. And then we've got 3 times 157. 12 times 13 is 157. No, 156 times 25. This next one, you can kind of reduce this. It's just 24 times 13. You can break it up however you want. That's how I broke it up. And you're just going to try and finish this up. I think this is 21. No, it's not. It's 26? Yeah, 156 over 6 is 26. And then over here, you can simplify this. This is like 36 to 1. Okay, so yeah, I might still need a calculator. I've got to multiply 2 times 36 times 169. I've got to multiply 3 times 26 times 25. I've got to multiply 24 and 13, and then I got to do the additions. So we'll go ahead and use the calculator for that part. But you can see I could easily design a problem on the test where you don't need a calculator, if just keep the numbers nice and small. Maybe having you plug in 12 was just too ambitious. Right? Okay, when this is all said and done, I ended up getting 13,878. Does that look right? Okay. Okay, so what we just saw was the first time you've ever seen this, I think, that you can manipulate sigmas a little bit, can't you? You can treat a sigma of a sum as a sum of sigmas. You can treat a sigma of a product as a product of a sigma. You can treat these sigmas as formulas, you see. So all of this kind of came down to a single number, of course. Nice, positive, big formula. Okay? So what is there left to learn? Well, the formulas I gave you all have something else in common. They all start with k equals what? 1. So this brings up a very important question. What if Mr. Shore gives me a problem that starts at k equals 5? If Mr. Shore changes this number down here, and he changes it from 1 to something else, these formulas do not work. You understand that? These formulas are designed for starting at k equals 1. Or, if we end up not stopping at n, we stop at something else. Are we allowed to use the formula? No. So we have to deal with that situation. And it's really not that hard to fix, to deal with. Let's take a look. Let's say that you're given this problem. You want to add k squared, not from 1 to 10, but from 6 to 10. So Mr. Shore's messing with you. Okay, I've changed the bottom number. It's no longer a 1. Now there are two ways to handle this situation. Okay, don't miss this. There are two ways to handle this situation. First, you could just pretend it's a 1 and do the problem. Watch. 10 times 11 times 21 over 6. And then you can reduce it. I think we did this problem earlier. Do you guys remember what it came out to? I'll just reduce it. See, this is 7 and 2. This is 5 and 1. Yeah, it was 385, I remember. Now, what's wrong with this answer? What's wrong with this answer? I added from I added from the first term to the 10th term. Is that what Mr. Shore asked me to do? No. So my answer is too, what? Big. Yeah, that's right. This answer is too big because Mr. Shore didn't want you to add the k equals 1, k equals 2, k equals 3, k equals 4, k equals 5 term. I didn't want those. I wanted you to start with 6. So we can fix this answer if we subtract off the sum of the first 5. K equals 1, 2, 3, 4, 5 was not supposed to be part of this problem, but we included it. So now we're going to subtract off sigma k equals 1 to 5 to sort of correct it all. Okay, so I'm going to erase some of my scratch work just so my solutions look a little tidier. This problem was done by doing 2 times 11 times 21 over 6, and we got 385, right? Now we're going to add up the first 5 terms, which would be found by doing 5 times 6 times 11 over 6, which is 55. And then we're going to subtract them. This is going to give me, of course, 330. And what does it represent? It represents terms 6 through 10. Why? Because I added all 10 terms, and then this means I'm going to take away the first 5 terms, leaving me with terms 6 through 10. So there were 10 numbers added. We didn't want the first 5, so we threw them in the trash can. That's what this step is. The first 5 numbers are thrown away. Okay, so this is super important because in calculus, we're going to change this symbol to this symbol, which has a very similar meaning. And we would play the same games with integral signs that we play with sigma signs. Okay? We treat them the same way because they sort of mean the same thing. They both mean sum. Big capital stretched S for sum, big fat Greek sigma for sum. Okay? So we'll play the same games with other calculus symbols later, limits and other things. But this is the first example where you've seen me manipulate 2 sigmas together. There's another way to do this problem entirely. The problem was Mr. Shore wanted us to add k equals 6 to 10 of k squared. We accomplished it by subtracting 2 sigmas. There's an entirely different approach, and it is just as important, if not more important. You might like it better. Why can't I just jump in and use the formula right now? It doesn't start at 1. I wonder if I could just make it start at 1. Watch. I'm just going to take away 5 right there. Can I do that? I'm just going to subtract a 5 right there. I can do that if I do this and this. Let me explain. Starting at k equals 6 and ending at k equals 10 is not the same thing as starting at 1 and ending at 5. That's not the same thing. But if we adjust all of the k's in the sum end by adding 5, everything stays balanced. Okay? I'm going to write that one more time, and I'm going to ask you to verify it real quick. Okay, what I'm saying is pretty bold. I am saying that the sum k through 6 of k squared is completely identical to the sum of 1 through 5 of k plus 5 squared. I am claiming these are identical problems. Help me out. How do you expand this sigma? You plug in what? 6, 7, 8, 9, 10. What's the first term? 36. What's the last term? 100. Good. Help me out. This means plug in 1, 2, 3, 4, 5. What's the first term? What's the last term? These are exactly the same thing. So how did I manipulate this sigma to make this one? I took away 5 from the bottom number, I took away 5 from the top number, and I added 5 to my k. Everything stays balanced. I increased the counter, and I changed the limits of counting. See? So now I can use the formula. Watch. Foil this thing out. And I'm basically doing my 2 formulas here. I don't know why I circled the 0 there. I meant to circle that. How do you add k squareds? You use the rule 5 times 6 times 11 over 6. That's how you're going to add up the first sigma using that k squared formula I gave you. Then you got an extra 10 there. So there is a 10 right here. But how are you going to add up the k's? You're going to use 5 times 6 over 2. That's the k formula I gave you, remember? And what are you going to do with this little 25er right here? Well, when you plug in 1, 2, 3, 4, 5, you're just going to get 25, 25, 25, 25, 25. That's just 125. You're adding up 5 25s. So this is just basically 125. And this, of course, gives us the exact same answer as last time, 330, because it's the exact same problem done a totally different way. Okay? Okay, so let's look again at these two problems, this problem and how I did it two different ways, okay? In the first case, okay guys, in the first case, I was given this problem and I noticed, oh darn it, it doesn't start at 1. So I said, well, that's okay. I'll just do it from 1 to 10. It's going to give me a number that's too big, of course, because it's got too many terms in it. And then I'll subtract off the first 5. Bam, bam, 330, I use the formula both times. Okay? So this method you might want to call subtractions of sigmas, because I don't know any other name for it. So subtraction of sigmas. Okay? The next method was entirely different. I transformed the problem. I didn't like the 6 to 10 look, so I made this a 1. How did I do it? I took away 5. But that means I have to take away 5 up here to keep the number of terms correct, which means I have to change the k to k plus 5 to keep things balanced. So I subtracted 5's here and here, added 5 to that k, and rewrote the problem entirely. We confirmed that this is the exact same sum. This adds up 36 through 100. This adds up 36 through 100. Then we expanded it and used our formula to solve. Totally different. I call this adjusting the index, because I honestly don't know what else to call it. Adjusting the boundaries or something. Adjusting the index is what I usually call it. Adjusting indices. You need to know both methods for calculus. Even though we probably won't do it with sigmas, we will do it with these symbols. Whether you're an A, B, or BC, you need to know it. Okay? Plus, it's just good, solid problem-solving skills, right? Okay, now, try this problem on your own. K equals 4 to 7. K cubed minus 3k plus 4. Try it both ways. I want subtraction of sigmas, and I want adjust the indices. So adjusting indices. Try it both ways. Of course, you should get the exact same answer both times. And I'll put the answer on here just so you have it, so you know you're doing it right. Okay. So your answer should come out to 698. Okay, so far you got this all set up. Now I'm going to work out the solutions for you. So hopefully you got 698. If not, see what you did wrong here. So first thing you do is treat this as k cubed in its own sigma. The k in its own sigma with the 3 out front, and then the 4 with its own sigma. So basically I'm taking the k cubed, the k, and the 4 as 3 separate sigmas. Here's your k cubed, the k, and the 4 as its own sigma. So I distributed the sigma symbol, you could say. Notice where the negative 3 goes. The negative 3 was here, but now it's in front of its own sigma. Okay, and all of these sigmas run basically from k equals 4 to k equals 7. Right? K equals 4, k equals 7. Okay, so now you're going to find basically 1 to 7. And then you're going to subtract off 1 to 3. So for the first one, you're going to run k equals 1 to 7, k cubed, and then there's a minus 3, and then it's k equals 1 to 7k, and then it's plus, and then it's k equals 1 to 7 of a 4. And then you're going to take that answer and you're going to subtract off the 1, 2, 3 case, because we're not really trying to go from 1 to 7. We're trying to go from 4 to 7. But first, let's get the numbers. So this is just going to be 7 times 8 all over 2 quantity squared. This is going to be 7 times 8 all over 2, not squared. And this is going to be just basically 4 times 7. So this is just 28. So hang on to that. Not done yet. Okay, now we're going to do the 1, 2, 3 case. So we're going to do sigma k equals 1 to 3, k cubed minus 3 times, and then sigma from k equals 1 to 3 of k, and then finally plus, and then sigma k equals 1 to 3 of 4. And this comes out to be 3 times 4 over 2 quantity squared minus 3 times, and then this is just 3 times 4 over 2, no square, plus, and then this is just 12, 4 times 3. So I'm just multiplying the 3 and the 4 for that, just like I did the 7 and the 4 up above. Okay, so that gives you this. And these need to be subtracted. So we're going to subtract the two expressions that I'm highlighting in green right now. This one and this one. We need to subtract those results. Okay, first we got to find them. So let's work this out. I need a little more space. I can always erase later if I use too much of the board here. So basically I have 56 over 2. So this is 28 squared minus, and this is 3 times 28 plus 28. And this is 6 squared minus 3 times 6 plus 12. So your calculator can get you these numbers. This gives us 728. So that's 728. And then let's do the other one. So it's basically 36 minus 18 plus 12. I don't even calculate for that. That's just 30. It's 30. And these get subtracted, remember? You're going to subtract these two numbers. And the reason is, again, you didn't really want to add 1 through 7. You wanted to add only 4 through 7. So you're going to do 1 through 7 and 1 through 3 and take a difference. Okay, so the difference is, of course, 698. As I told you, that would be the answer. So now let's go to another method entirely. So back to the drawing board. What we're going to do is we're going to adjust the index. We're going to start with the fact that they asked us to go from 4 to 7. And we're going to try really hard to force this so that it starts at 1. So what I'm going to do is I'm going to take away 3 here, and simultaneously add 3 to each k in the problem. So I'm rewriting the problem entirely. This now goes from 1 to 4, but now this is k plus 3 that's cubed minus 3 times k plus 3. So this is in place of what it used to say. It used to say k cubed minus 3k, but now I got a k plus 3 inserted for each of the k's in the problem. Okay, a FOIL will eventually get you down to this now. So k equals 1 to 4, and then there's a k cubed. After lots of work and collecting, I got basically a 9k squared. I have a 24k and a 22. That was kind of a lot of work to get that. I skipped the steps for you. And then now you're going to find the formulas for each. So to get the k cubed, you're going to basically do 4 times 5 all over 2 squared. So that's 100. To get the k squared, you're going to use 4 times 5 times 9 over 6, which comes out to be, let's see, 30. And don't forget there's a 9 in front of it, right? There's a 9 right there, so it's 9 times 30. And then to get the k, you're just going to use 4 times 5 over 2, which is 10, but don't forget there's a 24 right there, so this is 24 times 10. And then lastly, the 22, what am I going to do with the 22? I'm going to take this 22 times this 4, so that's just plain 88. Don't need a formula for that. You're just basically adding up a 22 4 different times is what that is. So 88 for the last term. And if you add all this together, you get 698. So aside from the FOIL, which I didn't show, this method would appear to be faster. It just depends on if you like foiling or splitting the sigmas, like we did in the previous problem.